we present complementary intrinsics from neural radiance fields and convolutional neural networks for outdoor scene relighting. The video shows a time-lapse artwork of Taj Mahal. The landmark appears with varying appearances because of the change of environment lighting. But, can we design an algorithm to independently manipulate the environment lighting and synthesize images with desired appearance? This is defined as outdoor relighting problem. Different from some other image enhancement methods, outdoor relighting intends to follow the image formation model, and synthesize the scene with intrinsic components in a physically aware way. The usual pipeline of outdoor relighting methods is first decompose the input image into some intrinsic components, replace the components related to environment lighting and leave others unchanged, then re-render the image from these intrinsics. However, the inverse rendering methods usually suffer from the lack of labeled real-world data, especially for outdoor scenes. Yu et al. Obtained supervision from cross-projection, which projects the image and predicted intrinsic components from one view to another and forms consistence losses. The same strategy can also be applied to the relighted images. However, the convolutional neural networks observe the paired input images only, which cannot make full use of the multi-view image dataset, and sometimes produce noisy or even undesired outputs. But neural radiance fields can overcome these defects. We now present our image formation model. Following Yu et al., we redesign the rendering function of neural radiance fields to accomplish physically aware rendering. The image is decomposed into albedo, shadow, and shading, while shading is derived from the environment lighting and surface normal. Similar to the RGB color function of vanilla NeRF, we model albedo with an individual MLP, which takes the 3D coordinates of sample points as the only input. Following the appearance embeddings of NeRF in the wild, we recover environment lighting as learnable embeddings. Each image is assigned with an individual embedding vector, with the shape of 3 × 9, representing the coefficients of second-order spherical harmonics. Surface normal is directly derived from the density function of NeRF, which might be not ideally smooth but enough for us. Finally, we employ another MLP to learn cast shadow from images, which depends on the 3D coordinates of sample points and the environment lighting. Apart from opaque objects, which means mainly buildings, ground planes in this situation, the color of sky background also needs to be formulated. The intrinsic-based imaging model is unsuitable for sky because the intrinsic of sky region is undefined. To complement the rendering procedure, we first need to know which region each pixel belongs to, either opaque object or sky region. Fortunately, the density function of NeRF provides an approximation of opaqueness. If a ray hits nothing, the accumulated density should be close to 0, which means the pixel is a part of sky. Then, we decide to model the color with an individual MLP, named Sky MLP. As the appearance of sky is only related to the lighting coefficients, and the ray direction indicates the particular pixel, Sky MLP only takes these 2 components as inputs. So far, the NeRF module can model outdoor scenes with intrinsic components, recover the intrinsics, and re-render the scenes. But it is really hard to acquire a NeRF from a single image in the wild. To accomplish the single image inference, we turn to CNN, which could take the highly accurate pseudo-labels of intrinsics, generated by our NeRF modules, as objectives during training stage. Though our Sky MLP is optimized together with other NeRF modules, in fact, it is decoupled from other MLPs and can be utilized during single image inference as long as all the inputs, ray directions and lighting coefficients, are aligned to the camera coordinate system rather than the world coordinate system. Our Sky module can generate significantly more realistic sky background than CNN-based methods. We now summarize the overall pipeline of our method. We build intrinsic-based NeRF from collected outdoor scenes, recover the albedo, shadow, normal for each 3D point. We generate pseudo-labels from fixed neural radiance fields and propose 2 CNN modules, intrinsic CNN for albedo, shadow, and normal estimation, and lighting CNN for spherical harmonics coefficients estimation. An individual Sky MLP is responsible for sky rendering. Composing the opaque objects and sky background, the image could be reconstructed. For NeRF modules, density function indicates the sky segmentation. And for CNN modules, a pre-trained semantic segmentation model is used. To relight a scene with target illumination, just manipulate the lighting coefficients, leaving other components unchanged. We collect 10 outdoor landmark scenes among POTA tourism dataset to form the training set. Apart from these, we also select 2 more scenes from Megadepth dataset for generalization capacity evaluation. Here we illustrate the estimated intrinsic components of our CNN module, our NERF module, and related work. R stands for reconstruction and S stands for shadow. As the figure shows, our method recovers better intrinsics. And here is the relighting results, compared to related work, which demonstrates the advance of our method. The evaluation is performed on both shadow-aware domain and shadow-free domain. In summary, we present a novel approach for outdoor scene relighting by complementing the intrinsics from both neural radiance fields and convolutional neural networks. We propose a new image formation model for NERF volume rendering, which handles static scenes and sky separately. Our method recovers accurate intrinsic components from NERF, and then these pseudo-labels enable our CNNs to estimate intrinsics from a single image. Outdoor scene relighting is conducted by editing the lighting coefficients in the physics-aware rendering procedure. Our method is completely driven by real-world data and demonstrates noticeable improvements over previous methods. Thanks for watching.